Hello, I'm Norman Wildberger, and we're here at the University of New South Wales. And I'd like to talk today about astronomy and trigonometry in ancient India. Okay, so this is a very interesting story. The Indian or Hindu civilization goes back a long time. We are talking at least 2000 BC. And we have, at least from around 800 BC to 200 AD, the developments of a primitive kind of mathematics. And notable amongst that early mathematics is a representation of the number system. So their representation, they had something called Brahmi symbols. This is around 300 BC. So we have 1, 2, 3. 4 was something like this, and 5 something like this. 6 is recognizable. 7, 8, 9, and then this is 10, and then something else is 20. That's like a circle. 30, 40, well, something like that. 50, 60. Okay, but notably, what's interesting here is that they had separate digits for the numbers 1 to 9. And this was a very, of course, important distinction that most other cultures didn't have, and ultimately let the Indians develop a very powerful arithmetic as time went on. And we've talked already in this series about the importance of the Hindu Arabic number system that we all use. That's a great gift that they've given to us. So the introduction of 0 happened quite a bit later, but nevertheless our current number system that we do arithmetic in is really originally a Hindu creation. Now their interest in astronomy also goes back quite a long ways, and it's often for similar kinds of reasons as we find in other cultures. So typically, calendars are always important. And we know that there's influences from further west. So Babylonian data arrived around 500 BC. So the Babylonians were really pioneers in systematically working through a lot of things. And then later on, Greek astronomy also came, 300 AD. And this is probably after the period of Ptolemy, but perhaps it's actually based on a prior work before Ptolemy's great work, the Almagest. So there's a lot of discussion and debate as to how much Indian mathematics was influenced and developed as a consequence of these other influences, and to what extent it was sort of a homegrown science. And the truth is probably some kind of combination of those two things, but we don't have as much information as we'd like. Yeah, there is a little bit of a difference. This one here has more of a wiggle, I guess, something like that. A little bit of a difference. And maybe we should say, the number system changed quite a lot. So there were quite a lot of variants on this, depending, if you go up 100 years or back 100 years, it'll look different. So there was an evolutionary aspect to these things that kind of evolved. Okay, so I suppose that officially Indian mathematician who really kicked off astronomy in a kind of official way was the great mathematician Aryabhata, who lived around 500 AD and wrote a very influential book on astronomy. So this book was eventually eventually went to Europe and had an influence there. It certainly influenced Arab work as well. So he has information about solar and lunar and indeed planetary positions. And there's things about predicting eclipses. And he has the remarkable computation that 1,582,237,500 rotations of the Earth correspond to 57,753,336 lunar orbits. So making a correspondence between the lunar orbit and the daily rotation of the Earth. And what this amounts to, if you divide this by this is really saying that a moon orbit takes 27.396 days, which is a very accurate kind of thing. So Aryabhata was one of the original Indian pioneers. In fact, he's celebrated, India's first satellite was named after him. So he also advocated a heliocentric view of things. So he had a heliocentric view. He knew that the Earth spun on its axis. And he was actually also instrumental, or one of the pioneers of introducing trigonometry into this subject. And I think that's really an interesting aspect of the Indian contribution. They liked calculating, and they were very good at calculating, and they developed very powerful technology for making calculations that went considerably beyond the Greeks. So this is a very interesting story. It's really a story of trigonometry. Trigonometry makes its appearance here really in the context of astronomical calculations, not in terms of the calculations that usually school children learn that trigonometry is used for. So trigonometry was really developed, and largely by the Indians and then also by the Arabs, to help understand what was going on with astronomy. But it was really coming from the geometrical understandings of the Greeks. So to understand things, we really have to appreciate that a sine table was a very powerful and important thing. You want to have a table of sines. And creating such a table is a highly sophisticated kind of thing. But it really goes back to Ptolemy. So Ptolemy, the great Greek astronomer, maybe 200 AD and so on, who wrote this famous book, the Almagest, which was a kind of a Bible for astronomy for almost millennia. So he had introduced, probably no doubt influenced by earlier Babylonian work, the idea of a chord of an angle. So you have a circle, and let's say it's of radius r, all right? And you have an angle, say, theta there. Then, associated to this, Ptolemy was interested in this length here, okay? So this length is called the chord of the angle. The chord of the angle. Now that's not a familiar kind of trigonometric function to a modern student, and it has been superseded by our understanding of sines and cosines and so on. And in fact, that was one of the things that the Indians did, is they took Ptolemy's tables of chords, and I guess at some point someone said, actually what would be a little bit more useful perhaps is given an angle in this domain to figure out what this perpendicular distance is. Okay, so that's not exactly a chord, but it's kind of like half of a chord of half of the angle. Now, so here's what the tables kind of look like. So we ended up having tables where, in modern notation, if there's the angle theta, then what was here was r sine theta. Not sine theta, but r sine theta. And r was typically a large value. Okay? So r was not equal to 1. That was too inconvenient. Okay. Rather, r was some bigger number that allowed the entries here to be less reliant on fractions and decimals. Okay, so like we're scaling up the usual unit circle so that we have more integer values floating around. So one popular value of r was 120, and another popular value that the Indians liked very much was 3,438. And why would you have 3,438? Well, the reason is that this corresponds to circumference of 360 times 60, which is 21600. And the reason why you want this to be the circumference is that if you have 360 degrees around the circle and each degree is divided into 60 minutes, then altogether around the circle you have 21,600 minutes. So that's actually, going back to the Babylonian measure, that's a convenient way of measuring circumference. And if the circumference is 21,600, then I guess the radius is close to 3,438. So they would have tables that were expressed like this. So for example, they would still write things in Babylonian form. So 3 degrees and 45 minutes, and then there would be a value 751. Things are expressed in Babylonian style. 730, 1540, and so on. So if you looked at a table at that time, you wouldn't see nice values of theta like 1, 2, 3, and so on. You would find these rather irregular values of theta. And this goes back to the ancient Greeks. So Hipparchus already, and that's like 100 BC and earlier, he had tables using multiples of 7 degrees, actually of 7.5 degrees. And the reason why 7.5 degrees is relevant is because 30 degrees is easily obtainable geometrically. It's just half of a equilateral triangle angle. And then if you bisect that, which you can easily do with Euclidean methods, then you get 15 degrees, and if you bisect once again, then you get 7.5 degrees. And if you bisect, in fact, once more, then you get 3 degrees and 45 minutes. So the origins of these tables were really based on geometrical constructions going back to the ancient Greeks in terms of what kind of angles you could create by bisecting. So in India, then we find this transition from the Ptolemy kind of view of having a chord as being fundamental to a more familiar picture that undergraduates will recognize. So this is an arc of a circle, and this quantity here was called the jya, and that's like the sine, And here is the collegia. That's the cosine. And this quantity here also had a name. It was called the utkramaja. Okay? And that corresponds to what we, well, recently, until recently in European work, it was often called the verse or versed sine of an angle, which was 1 minus cosine theta, sometimes called a versed sine. So for some kinds of trigonometric calculations, this versed sine is actually quite useful. So Aryabhata was able to compute sine tables in a very clever way. And then the next development, I guess, that we can talk about is Bhaskara, who was, actually there's two Bhaskaras that figure prominently in Indian mathematics. Bhaskara number 1 lived around 600 AD. And he came up with this beautiful formula that I've probably mentioned in this series at some point, but I'll mention it again, that if here is the sine function, okay, in degrees, of course, because radians only came into the picture much, much later. Radians have only been around for about 150 years. So up till then, it was all Babylonian degrees. So here is the sine function, but actually it's what we would call r sine theta, where the top value is this 3438. All right, so there's the sine function, and it's crucial to be able to calculate what that thing is, and that's what these sine tables do for us. But Bhaskara realized that you could find a quadratic approximation, or kind of quadratic rational approximation. So some kind of function that something that looks very much like the sine function, but whose formula is, so r sine theta here is 4 theta times 180 minus theta. Oh, I guess we have to multiply by r. So it's r times this 4 theta over 180 minus theta divided by 40,500 minus theta times 180 minus theta. So this is a rational function of theta, which does a really good job of approximating sine theta in the range from 0 to 180, and that was discovered around 600 AD. Okay, another development that happened is that if we look at a regular pentagon has angles of 36 degrees involved. So by studying a regular pentagon, we get understand 36 degrees and also 18 degrees. So the second Bhaskara II, who lived 500 years later, around 1100 AD, very prominent Indian mathematician who lived in Ujjain. He really was responsible for the first work devoted to trigonometry in India. So, and amongst the kinds of things that he was able to understand, he knew that sine of 18 degrees was root 5 minus 1 over 4, very closely connected with the golden ratio, naturally enough, because it's intimately connected with the pentagon. And sine of 36 degrees was square root of 5 minus root 5 on 8. And these are interesting formulas that augment most undergraduates' understanding of, sine of 30 degrees, 45 degrees, 60 degrees. So this is really going beyond and making it bigger, what kinds of things we can talk about. So once we have 18 degrees, and we have 15 degrees, well, then the difference is 3 degrees. Okay? So once you have these kinds of formulas, you can calculate the sine of 3 degrees. And Bhaskara knew the addition formulas for sine. So sine of A, or alpha plus or minus beta, is sine alpha cos beta plus or minus cos beta, or cos alpha sine beta. There we go. All right, and so from this, we could get, if we know sine of this and we know sine of this, then we can calculate sine of 3 degrees. So sine of 3 degrees is known. So then to get a really nice table, what you want to do, you want to find sine of 1 degree. Find sine of 1 degree. Well, so it turns out that there is a very clever way of doing this that might be familiar to you from the following formula. You'll all know that sine of 2 theta is equal to, 2 sine theta cos theta. And there's a less well-known formula. That's sine of 3 theta equals 3 sine theta minus 4 sine cubed theta. This is a formula that we learn in first year here in linear algebra. Okay. This exhibits sine 3 theta as a cubic polynomial in sine of theta. It's a cubic polynomial in sine of theta. And in particular, if we know sine of 3 degrees and we want to know what sine of 1 degree is, it's really the same as calculating the zero of this cubic polynomial. Right? So finding sine of 1 degree involves solving a cubic. And Bhaskara was able to do this. He had a very clever way of solving this particular cubic. He didn't have a general formula for solving cubic, but he could do some clever algebraic manipulations to get a good approximation for the zero of this thing. And so he was able to find a sine of 1 degree. And then from there, we get very nice, beautiful sine tables. And we're talking 1100 AD, so this would have been hundreds of years before European mathematicians were at this level. But around this time, Arab mathematicians were also investigating these kinds of things and also made important contributions, and I'll talk about them later. There's another important figure that we've mentioned before, Brahmagupta. Talked about one of his formulas for areas of cyclic quadrilaterals. He was also a notable astronomer around 600 AD. And perhaps he was the first person to understand the law of sines in the following context, that if you have a right triangle with, say, an angle alpha here and an angle beta here, and say that side is capital A and that side is capital B, then he knew that sine of alpha over sine of beta equals A over B. That's a special case of the law of sines, but it's pretty close. And it's reasonably easily extendable to a general triangle. The law of sines. But in fact, a lot of the trigonometry that was really needed was spherical trigonometry. When you're doing astronomy, you want to work on the celestial sphere, and so you are interested in problems where you have, on a sphere, maybe you have there's a north pole here, and you have some point here whose angle there you know, and maybe here's another point. Maybe you know that angle, so maybe you know this angle and you know this angle, and perhaps you know this angle as well. And then maybe you're interested in what is that quantity there. That's a kind of spherical triangle kind of problem that if it was a planar problem, you could use planar trigonometry. In this case, maybe like a cosine law. But since this is all happening on the surface of a sphere, you need actually spherical analogs of those more familiar planar formulas. And so this spherical trigonometry actually plays a very natural role, and perhaps a bit surprisingly, a lot of the classical formulas of trigonometry that you learn in school were actually investigated in this spherical situation first. They were actually investigated in this spherical situation first. So the Indians made some contributions here, but also the Arabs made very important contributions to this topic here. So I want to finish our discussion by going a little bit forward in time to around 1300 and a very remarkable mathematician, Madhava, okay, who lived in Kerala, which is a province. There's India, and a sort of province down here somewhere in India, and he taught in an illam, which is some kind of family compound. And he had followers who would live there too. And the followers basically memorized the teachings by creating them into verse. So the teachings were transmitted by verse. But he was very far ahead of his time in some ways. So he was able to come up with formulas that, very, very important formulas that are actually familiar to most undergraduates. In particular, the power series for cosine, which is 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, and so on. So factorial here means like 5 factorial is 5 times 4 times 3 times 2 times 1. And the corresponding formula for sine is theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, and so on. So he had a very clever, almost calculus kind of argument. He talked about approximations, and he sort of concocted these things successively. So these are obtained by a careful study of differences. And these are usually ascribed to Newton. So Newton came up with these power series, but that was fully 300 years later. So these are really Indian formulas, quite remarkable ones. And I'd like to just finish with one more of his formulas, which also is a beautiful formula, that if you have a circle with circumference C and diameter D, C is the circumference and D is the diameter, then his formula is that C is equal to 4D times 1 over 1 minus 1 over 3 plus 1 over 5 minus 1 over 7, and so on. And it's easily seen to be equivalent to the formula that pi over 4 equals 1 minus 1/3 plus 1/5 minus 1/7, and so on, which is usually called Gregory's formula. Gregory's but that was 300 years or so after Madhava clearly enunciated it. So the Indians had a very strong orientation towards arithmetic. They were really good calculators. They had in possession the best arithmetic system that's around in the ancient world, and they put it to good use. So they calculated all kinds of interesting and important things, and so the history of trigonometry really is to a large extent very much developed with the aid of the Indian contribution. But we have to also look at almost the adjacent civilization, the Arab civilization, which interchanged a lot of ideas with the Indian one, and that's what we'll talk about next time. They also made very important contributions to trigonometry.